Okay. Hello, everyone. I'm Selim Zoorob. I'm a biophysics student at UC Riverside.
Hi, and I'm Sahil Bhalla from UC San Diego.
We decided to work on problem 2, which is the sticks and stones.
So I guess first we're going to discuss the prompt, which is using sticks on seesaws to create various logic gates and circuits. So the way we interpreted this to make it easier on ourselves and to try and stay most within the spirit of the problem, we, instead of having them actually be gravity-based seesaws, we put the toothpicks on a 2D plane with the bound in the center. So effectively they work like seesaws, although it would be kind of hard for anyone to sit on them. So the way these seesaws work, as explained in the problem, is once for each side being low represents a binary value of 0 and high represents a binary value of 1. And an individual seesaw has two sides. So effectively each one is a NOT gate, which flips the input with one side being 0 and the second side being 1. So one of our goals is to create the various logic gates using these seesaws. So yeah, so here's the truth tables of some logic gates, and a logic gate pretty much is a machine that accepts a single or multiple binary inputs and returns one or more, or usually one binary output. So the ones we're focusing on for our project are the NOT gate, the AND gate, the OR gate, and the XOR gate. And you can see the truth tables here with the two inputs and the output. Now the NOT gate, as I just showed you, is pretty easy. It's already there with just the basic seesaw. But the question is, how do you make two input gates out of toothpicks on a 2D plane? Now, the way we accomplish this is using a simplification. So as you may have noticed, in the truth tables of the previous logic gates, the inputs are symmetrical. So it doesn't matter the order of the inputs, it returns the same output. So the input of a 1, 0 is the same as the input of a 0, 1. Now, since the way we've modeled it, we're not having the entire machine be connected together mechanically. And in fact, the gates themselves are mechanical, but we have to use our hands to connect the different gates together. We can actually switch 0, 1s or 1, 0s to 0, 1s manually, meaning we can ignore the 1, 0 inputs since they're effectively always give the same outputs as the 0, 1s. Now, I used a technique called Carnot maps to use these to simplify the basic AND, OR, and XOR gates, and simplifying them from A and B to A. Because if you can ignore the 1, 0 input, the result of A and B is simply just the value of A. For example, 1 and 1, well, if it can't be 1 and 0, it'll always be 1 and 1, so the input is always just A. And then similarly simplified A or B and A XOR B. Now we can use these simplifications and simplified gates to create a 4-bit adder. So this 4-bit adder is created out of components called full adders, which is shown at the top right of the screen. So these those top two gates are XOR gates, and the flat-sided gates are AND gates, and the rightmost gate is an OR gate. So this is the schematic for an adder, and in a full adder adds 2 bits plus a carry. So it adds A, B, and a carry, and computes a sum and a carry out if there is one. For example, 1 plus 0, the sum would be 1, the carry out would be 0, and 1 plus 1, the sum would be 0, and the carry out would be 1. So these are the formulas to compute the sum and the carry out from the inputs. And a 4-bit adder is just 4 full adders connected together with the carry out of the first adder going into the second one. So it computes a sum of 2 4-bit numbers, effectively the same way you do it by hand, by carrying over the extra value each time from the lowest significant bit to the most significant bit. And now on to the actual mechanical design of how we did this 4-bit adder.
So we wanted to be practical as much as we could. So instead of making a 4-bit adder, what we did was 1-bit adder that could be that's extremely modular. And by that, I mean, instead of having a 4-bit adder that's just a 4-bit adder, we made a 1-bit adder that could be added up until infinity, basically. So if you need a 5-bit adder, just need to add 5 of those and you end up with a 5-bit adder, let's say. And we came up with this design where basically you have your initial inputs A and B, and Cn is the carry out. The Cn by default at the beginning is equal to 0, and then let's say on the first bit is equal to 0. On the second bit, it depends on the value that we obtain from C out. I wanted to show how physically we have done the XOR, the and the OR mechanisms. Basically, that's how we did physically. We did them physically. The lines are toothpicks, and the red dots are like pivots where they like rotate. So you can see that so basically the first number is A, and I've said that we swap A equals 1, B equals 0 to A 0, and B equals 1, and that took us like a while to like figure out how to like make it optimal for us so that it could work. So basically we decided with A being the first term that we treat and B the second term that we treat. With AND, this is the outcome. With OR, it's basically the inverse of the and with the XOR we came up with a brilliant design of making the B a smaller membrane. So let's say if it's 1 1, then technically you should end up with a 1 here, but the B the B membrane will push the mechanical membrane over here and will force it to go to 0 since it's the second treated membrane. And I'll show that furthermore when I cover the actual experiment. This is the design we worked on. As you can see, it's quite big, but it's basically everything that we have covered over here, translated into a carton. Yeah, so basically that's how we managed to make it. And I marked the first beginning variables with like a star to know that we're gonna first read this binary. So yeah, so basically I wanted to show you an example of how it works. So if we add 0 and 1, you can see that it's like stop motion picture. So I'm going line by line. So we obtained D equals 1, and then over here we obtained S equals 1, and then we obtained E equals 0, and then F equals 0, and the carry out is 0. So basically the final result is that's the video of me physically doing it. So the final result is we obtained 1, and the by default we set Cn equals to 0, and we obtain the carry out equals to 0. Yeah, I just want to show you how I did it physically. So yeah, that's how we did the programming, and Sahil will cover it.
So yeah, okay. So for programming, I just pretty much the formulas from earlier I showed we just kind of computed them literally in C++. So we made the swap thing that when we swap 1 0 to 0 1s as this int swap thing, and effectively we just translated directly into code.
Unfortunately, your time is up.
Okay.
Yeah.